long straight metal rod has a radius of 4.4 centimeters and a charge per unit length of 35.4 nanocoulombs per meter. Find the electric field at the following distances from the axis of the rod, where distances are measured perpendicular to the rod's axis. A. 3.10 centimeters, B. 15 centimeters, and C. 150 centimeters. Alright, so right here in the middle, this is our long, charged, straight rod with a radius of 0.0440 meters. And around it, outlined in yellow here, is the appropriate Gaussian surface of this charged rod. It is the same, it's another cylinder, but with a bigger radius of length r, which we will use in our calculations. And for part A, it asks us to find the electric field at point P when it's 0.0130 meters away from the axis of the rod. Now you might be tempted to just go use the whole EA is equal to Q over epsilon naught type of deal here. But if you take a look closely here, this distance is actually shorter than the radius here. So actually, right here, this point is right here. I'll label it A for part A. As we know, inside any conductor, the electric field is zero because all the electric field lines would sum to zero. So for part A, the electric field is zero, and therefore doesn't have a direction because the magnitude is zero. And point B asks us to find the electric field at point B, which is 0.15 meters. Now here we're going to use our equation for electric flux, which is equal to EA, which is also equal to the charge enclosed over epsilon naught. Now we're solving for the electric field here, so I'll divide both sides by the area. And now we're going to plug in what the area is, but here for the area, because it is the lateral surface area of a cylinder, I'm going to plug in 2 pi RL. And the problem tells us that the rod has a charge per unit length, and it gives us the value. Q per L, charge per length. So I'm going to substitute Q over L for lambda. And now we have our general equation for the electric field. We plug in our radius of 0.15 meters, and the problem tells us that lambda is equal to 35.4 nanocoulombs per meter. We get that the electric field is equal to 4.244 newtons per coulomb. Now for part C, it's very similar to part B, except the point is all the way out here at a distance of 1.5 meters away. Now if you're thinking, can't I just take that and substitute it in for this distance down here? You're absolutely right. So with that equation, E is equal to lambda over 2 pi r times epsilon naught, we just plug in our 1.5 meters for the radius. And here our electric field turns out to be 424 newtons per coulomb. Now it's interesting to note here that from part B to part C, you increased the distance away from the center of the rod by a factor of 10, and as a result, the electric field down here decreased by a factor of 10. And that's because our equation here has only r on the bottom, not r squared. If it was r squared, it would follow the inverse square law, and an increase by a magnitude of 10 would result in a decrease by a magnitude of 100. Since there's only one r down here, it's a linear decrease. Side note, the electric fields at points B and C both point to the right, since there's a positive charge contained in the rod,
and electric field lines always point away from a positive charge.
Now, when I was first doing this problem, at first I could not figure out what the electric field was for part A, because I tried doing this whole Gaussian equation thing and I was getting some weird answers, and I realized that it's still inside the conductor, so that the electric field was just zero because all the electric field lines sum to zero. And then for part B and C, when I actually did get around to doing the EA is equal to charge enclosed over epsilon naught, I would get to right here and I would think, like, they didn't give me the charge and they didn't give me length. What do I do? And then I realized that lambda is equal to dq over dl, which is also just equal to q over l. So then I realized I could substitute that in, and then I could plug in the numbers and get an answer. And this problem shows my growth because it shows that I understand the concept of magnetic flux, and I'm able to quantitatively manipulate it to solve for the electric field. Also, it shows that I understand that the electric field is always zero inside of a conductor. Thanks.